In this video, we are going to talk about vector subspaces. This is our overview slide, which we'll spend 5 minutes or less over, and then we'll go through each topic in more detail and with more examples. The first thing we'll do is review what it is to be a vector space. Remember, a vector space is a set of vectors along with an addition operation on the vectors and a scalar multiplication where we have a scalar multiplying a vector. And these are the properties that need to hold in order for the set of vectors with the two operations to be a vector space. We need that vector addition and scalar multiplication to both be closed. We need the addition to be commutative and associative. We need additive identity, in other words, a zero vector that when you add it to any other vector, it gives back your any other vector. We need an additive inverse. And we need for our scalar multiplication both to be distributive and also associative. The main topic of this video are subspaces. So a subset U of V is called a subspace of V if U is also a vector space. So if U is a subset of V, remember V is a set of vectors along with our two operations. So we take some subset of our vectors V, and that subset is U. So if U on its own with the operations of addition and scalar multiplication is a vector space, then we say that U is a subspace of V. We get a lot of these algebraic properties like commutativity and associativity. We get that carried over because it's true of all vectors in V. So we only need to check three things to verify that U is a subspace of V, assuming U is a subset of V. The conditions we need to check are one, that the additive identity is in U, and second, that the closure of addition and closure of scalar multiplication still hold in U. And we'll do this example here, where we say if B is in our field, and in the field we can either have real numbers or we can have complex numbers. So instead of like F and F4, I like to think of R4. So for F4, the difference between F4 and R4 is R4 are real numbers, and F4 can be real or complex. So in F4, we have this 4 tuple, the x1, x2, x3, x4 vector. And it is the vector x1, x2, x3, x4, where x3, the third coordinate, is equal to 5 times x4 plus a constant b. And we want to check or verify that this is a subspace of F4 only if b equals 0. Here I've written out what our vector, our subset looks like. It looks like we have a first coordinate of x1, a second coordinate of x2. Our third coordinate is equal to 5x4 plus a constant b, and then x4 is our last coordinate. The first thing we need to do if we want to check to see that this subset is a subspace is we need to verify that the additive identity is in this subset. So the additive identity for R4 or F4 is 0, 0, 0, 0. This is the vector. When you add it to any other vector, you get back that any other vector. In this case, if x3 is equal to 5x4, and x4 needs to be 0, then x3 equals b. And so for x3 to equal 0 here, that must mean that b must equal to 0. So the additive identity is in the subset only if b equals 0. Second, we need to check the addition and verify it is closed. So addition is closed. We take a vector x of this form. So we have x1, x2, 5x4 plus b, and then x4. We take a vector y of this form. So we have y1, y2, 5y4 plus b, y4. And we do our vector addition, which is coordinate by coordinate addition, and we get x1 plus y1, x2 plus y2, 5 times x4 plus y4 plus 2b, and x4 plus y4. So we can see now over here that x3, the third coordinate, needs to equal to 5x4, which it is. It's 5 times this fourth coordinate plus b, but what we have is 2b. So the only way this 2b can equal to this b is when b equals 0. So again, addition is closed only if b is 0. We do something similar for scalar multiplication. We multiply A times our representative vector, x1, x2, 5x4 plus b and x4. Multiplying in, we get ax1, ax2, 5ax4, and ab, and ax4. So we want our third coordinate to be equal to 5 times x4 plus b, but we see it's equal to 5 times ax4. That's good. But we have an a times b, so the only way a times b is equal to this b here for any value of a, any scalar of a, is if b is equal to 0. So again, scalar multiplication is closed only if b is equal to 0. So we have this subset then as a subspace only if b equals 0. The last topic we have are the sum of subsets and a direct sum. So the sum of subsets says, suppose we have sets u1, u2 up to um. They're subsets of V, a vector space V. Then the sum of u1, u2 up to and we denote that with u1 plus u2 plus up to is the set of all possible sums of the elements u1, u2 up to where we have the first vector u1 is from the set u1, the second vector is from the set u2, up to the vector is from the set We'll do examples of sum of subsets in the main part of our video. So the next thing we have are direct sums. So suppose we have our sets u1, u2 up to they're subspaces of V. Then the sum, this sum of subsets, is called a direct sum if each element of our direct sum can be written in only one way as a sum of vectors u1, u2 up to where the u sub I over here come from the set u sub I. That concludes our overview. I'm going to skip going into detail of this review since this was the topic of our last video, and we're going to start in detail with the idea of a subspace. The definition of a subspace is given here. A subset U of a vector space V is called a subspace of V if U is also a vector space. So the idea is we have a vector space V. So it's a set of vectors. Remember, V is a set of vectors along with our vector addition and our scalar multiplication. Now if we take a subset of U, so that is we take a subset of these vectors, we keep the two operations, our scalar multiplication and our vector addition. And then if U is also in its own right a vector space, then we call it a subspace of V. In our previous video, when we wanted to show something was a vector space, we had to show that the vectors along with our addition, our vector addition and scalar multiplication satisfied all 9 of these properties. So it was quite a lot of work to do, or many steps to do. However, when we want to show that U, if it's a subset of a vector space V, if we want to show it is a vector space, the work is much smaller. And the reason is because we're inheriting our two operations, our vector addition and our scalar multiplication. And many of these properties have to do with our operations, so they come automatically because V is a vector space. In particular, these 4 properties here, addition is commutative, addition is associative, our scalar multiplication has distributive properties, and our scalar multiplication is associative. These 4 are just properties of these operations that we inherited from V. So if V is a vector space, those operations still have those algebraic characteristics even for the set U. So these 4 we get for free because U is a subset of V, so we don't have to prove them. These 2 here, additive inverse and scalar multiplicative identity, they come because of closure, which we're going to have to prove. But once we prove closure, these 2 come automatically. Essentially, let me just show you something with the additive inverse. Essentially because if we have, once we have our addition identity, our additive identity, we're going to have to be able to do 0 minus a vector V has to be able to give us our inverse. And this vector, our inverse, needs to be there if we have closure. So there's only three things left that we need to prove to show that U is a subspace. First, we need to show that the additive identity, this one here, exists in the set, in this case U. And second, we need to show that addition is closed. And last, we need to show that scalar multiplication is closed. And so next, we have many examples. Our first example, this is the one that was on our overview slide. So if B is in F, it's in our field, so it can be a real number, it can be a complex number. Then this 4 tuple x1, x2, x3, x4, and f4, such that x3, this third coordinate, is equal to 5 times the fourth coordinate plus b, is a subspace of f4 only if b is equal to 0. And here I've written out what our vector looks like in this column format. So I have my x1, my x2, my x3 now is 5x4 plus b, and then over here I have my x4. The other thing I'm going to say, sometimes you might feel more comfortable instead of the f4. If you want, you can think of this as r4. And then at the last minute you can say maybe they're complex numbers, so then you change it to an f4. But they really look the same. So I've cleared out some space. I cleared out that huge thing about what we need to prove for a vector space, and I left our three conditions we need to prove for a subspace. And here's our problem. Again, we wanted to show this x1, x2, x3, x4, where x3 is equal to 5x4 plus b is a subspace only if b is equal to 0. And this is what our vectors look like: x1, x2, 5x4 plus b, x4. The first thing we need to do is show the additive identity is in our subset. So our additive identity in R4 is the 0 vector, 0, 0, 0, 0, right? This is the vector that you can add to anything and get back that anything. In our subspace, this x3 is equal to 5x4 plus b. So I've written that here. This x3, this third coordinate, is 5x4 plus b. In this case, x4 is equal to 0, so it's 5 times 0 plus b, which implies for x3 to be 0, in order to be the identity vector, then b must equal to 0. So the identity is in this subset here as long as b is equal to 0. The next property we want to show is that addition is closed. So here I have my first vector, x vector, in this form. So we have x1, x2, 5x4 plus b, and x4. And then I have a y vector also in this subset. So y1, y2, 5, y4 plus b, y4. I add these two vectors, component by component or coordinate by coordinate, x1 plus y1, x2 plus y2, 5x4 plus b, plus 5y4 plus b. I can factor out my 5 and I get my x4 plus y4, and then I have my 2b. And then I have my x4 plus y4. For addition to be closed, this x3 coordinate must be equal to 5 times my x4 plus b. In this case, x4 is x4 plus y4. But what we have is 5x4 plus y4 plus 2b, so the only way 2b can be equal to b, so the only way this 2b is equal to this b, is if b equals 0. So I have that notated here. Addition is closed if b equals 0. I should also put this here, that the identity is in our x1, x2, x3, x4 if b is equal to 0. Last, we need to show that scalar multiplication is also closed, or the closure of scalar multiplication. So I take a scalar a, and I'm going to multiply it times my vector x1, x2, 5x4 plus b, x4, and I get ax1, ax2, 5ax4 plus ab, and ax4. So remember a, this needs to be true for any scalar a. So it's not that a is equal to 0, or it's not that a is equal to 0. It has to be true for any scalar a. So in this case, our third coordinate needs to be equal to 5x4 plus b. But what we have is 5ax4, so this part is good, but we have ab is equal to b. And this is true for general A only if b is equal to 0. So what we've shown is the three conditions for a subspace, or you could say two conditions if you consider the two closure conditions one condition. But the three conditions, I'm going to consider the two closures as two separate. The three conditions are met only when b is equal to 0, and that's exactly what we were asked to show. Our next example is the set of continuous real-valued functions on the interval 0, 1 is a subspace of R to the 0, 1. The first thing we want to do is figure out this notation, and this notation is from our last video. So remember in our last video, we said that f to the s, this is a scalar field, so you can consider this the real numbers or the complex number to a set S. This notation here, f to the s, is the set of functions from the set S to the field F. And we had this as an example of a vector space. So kind of looking at this, I'm going to erase these because it isn't relevant for this discussion. So the idea is we have some set S, and we're mapping to F. So if F is the real numbers, we'll map to the real number line. So we're going to take elements of S, map it to the real number line. So our vectors are these functions that map from S to the real number line. And then we said that our vector addition then was normal addition of functions, where f plus g of x is equal to f of x plus g of x, and our scalar multiplication is our normal scalar multiplication of functions. So a scalar a times f of x is equal to a times f of x. Looking now at this r to the 0, 1, r to the 0, 1 is the vector space of functions where the functions f go from the interval 0, 1 to the real number line. And the picture is going to look like this. F of x maps things from this interval, this closed interval 0 to 1, to the real number line. And one thing to remember is this vector space here, it's the set of all functions, so there's infinitely many ways of mapping this interval to the real number line. So I've cleared out some space again by taking away my vector space definition, but leaving my conditions for a subspace. We have our R0, 1, that's the vector space of functions that map from the interval to R, and we're showing that the set of continuous real-valued functions on the interval, so our functions, this is a set of functions f of x that map from the interval, and they're real-valued functions, so they map to the real number line, where f of x is continuous, and we want to show that this set is a subspace of R to the 0, 1. The first thing we need is the additive identity. So when we're mapping from 0, 1 to R, the identity function is I of x is equal to 0, because when you add this to any other function, you get back your original function. And I just noted that here. If you add f plus I of x, you get f of x plus I of x, and you get back your original function. That's what makes this the identity function. Now, the additive identity, this function is continuous, and it's a real-valued function. And so this function here is in our set f of x going from 0 to 1 to the real number line and is continuous. We need to show that the closure of addition, so let's say f of x goes from 0 to 1 to r and g of x goes 0 to 1 to r. These are both, and let's assume they are both continuous. Now when we add f and g, we get f of x plus g of x, and this is a real number since the sum of these two reals, because remember f of x gives you a real and g of x gives you a real, the sum of two reals is a real, and the sum of these two continuous functions is still continuous. So we are still, we've shown that addition is closed. And last, we need to show the closure of scalar multiplication. So when we have AF of x, we can pull out our constant. This is just a property of functions. So pulling out our constant AF of x, this is real because we have two real numbers. Our A and our F of x are both real, because multiplication of two reals is real. And also our AF of x is still continuous because you can scale a continuous function and you're still continuous. So our three properties are verified, and we have verified the set of continuous real-valued functions on the interval 0, 1 is a subspace of R 0, 1. Our next example, are all subsets of a vector space a subspace? The answer is no. And to illustrate this, consider a vector space V with a set of vectors, and now remove the additive identity from the set of vectors. So you'll have a subset of V, that is all the vectors except the identity, but you will not have a vector space. So since it's not a vector space, it will not be a subspace. Our next example is to show the set of differentiable real-valued functions f on R is a subspace of R to the R. First, this R to the R, that's the set of all functions f of x that maps the real numbers to the real number line. I'm going to call this subset here the set of all differentiable real-valued functions f on R. I'm going to call that set V. So that's the set f of x that maps from R to R. It's a function on R, that's what gives me my domain, and it's a real-valued function that gives me my range. And they're differentiable, so I want to say that f prime exists. This sort of reminds me of our last example, except instead of saying differentiable, it was continuous. Again, I've cleared out our space and said we're looking to show that V is a subspace of RR, and V is the set of functions f of x that maps the real numbers to the real numbers, and it's such that f prime of x exists. The first thing to show is the additive identity. That's the function that maps everything to 0, right? That's the function when you add it to any other function, you get back the original function. So we want to show that this is part of V. Well, so the derivative of I of x is equal to 0. We've shown that the derivative exists, it's differentiable. So I of x is differentiable and it's in V, so the additive identity is in our subset. Next, we need to show addition is closed. So I'm going to be given f of x, that's a function going from R to R where f prime exists, and then I'm going to have g of x going from R to R such that g prime of x exists. Now I can consider adding these two functions f and g. So f plus g of x, that's just equal to f of x plus g of x. Now I can take the derivative f plus g prime of x. And from our properties of derivatives of functions, if we have the sum of two functions, we can take the derivatives separately. So I have f prime of x plus g prime of x. Since f prime of x and g prime of x exists, then their sum exists, and therefore f plus g prime of x exists, and this is in V, so addition is closed. Finally, we need to look at scalar multiplication and show it's closed. So again, I have my f of x, it goes from R to R, and f prime of x exists. So if I multiply c times f and take the derivative of x, as you know in derivatives, you can always pull out your constant c. So then I have c times f of x is in R. So f prime of x exists. So c times f prime of x also exists, and it is in V. So we have shown our three properties hold, and therefore our subset V is a subspace. So what we have shown is a set of differentiable real-valued functions f on R has the additive identity, addition is closed, scalar multiplication is closed, and therefore this set here is a subspace of R to the R. Our next example is the set of differentiable real-valued functions f on the interval 0 to 3 such that f prime of 2 equals b is a subspace of R 0, 3, if and only if b equals 0. So this is sort of a combination of a couple of previous examples we did, but we're looking at functions f that map the interval, the open interval 0, 3 onto the real numbers. And I should also note that the derivative, so that also implies that f is differentiable, the derivative at 2 will equal to b. The first thing I need to check for is the additive identity. So for functions, the additive identity is the function that assigns 0 to every value of x. So I of x, our identity function, goes from 0 to 3 to R, and I of x is equal to 0. So you can verify, right? I of x plus any function f of x will give you back f of x. We want to note then that I prime at 2 is equal to I prime at x, which is equal to 0, right? The derivative of this is 0, so the derivative at 2 is equal to 0, which means that the additive identity is in this subset only if b is equal to 0. Next, we want to verify addition is closed, so we're going to let f be a function that maps from the open interval 0 to 3 to r, and f prime of 2 is equal to b. Similarly, g of x maps from 0 to 3 to r, g prime of 2 is equal to b. When we consider now f plus g of x, that's equal to f of x plus g of x, then f plus g prime of x will be equal to f prime of x plus g prime of x. So f prime of x is equal to b, and g prime of x is equal to b. Therefore, f prime of x, and this should be a plus g prime of x will be equal to 2b. For f plus g prime of x to be equal to b, and that's what we need in order for addition to be closed, if we also have that it's equal to 2b, so these two statements are only true if b is equal to 0. So we have noted that addition is closed only if b is equal to 0. Finally, we need to verify that scalar multiplication is closed. So we have our f going from 0 to 3 to r, and its derivative evaluated at 2 is equal to b. Now when we multiply our function by a, so our new function af of x, when we take the derivative of af of x, we can factor out the constant a from our derivative, and so we have a f prime of x, which means the derivative, since the derivative of f of x is equal to, at 2 is equal to b, I should put this as a 2, because it's not just, let's see if I can get this, 2, is equal to a times b. And in order to be part of our subset, the derivative evaluated at 2 needs to be equal to b. So this is only true if b is equal to 0, because remember, a is an arbitrary constant. It's not a specific constant 0, but any constant times a equals b is only true if b is equal to 0. So here we have shown that this subset is a subspace only if b is equal to 0. So what we have shown is the set of differentiable real-valued functions f on the interval 0, 3, such that f prime of 2 equals b is a subspace of r to the 0, 3. Our next example is the set of all sequences of complex numbers with the limit 0. And we want to show that this is a subspace of c to the infinity. And in case the c to the infinity looks strange, it's actually an example from our last chapter, which I don't think I covered, so I'll look at it now. So this f to the infinity is a sequence of numbers in our field. So if f is r, it's a sequence of real numbers. If f is complex, then it's a sequence of complex numbers. And we have x1, x2, x3 up to infinity. And we have our addition of these sequences as it looks like vector addition. It's component by component. So if we have this infinite sequence of real numbers here, infinite sequence of real numbers, then to add them, we add x1 to y1, x2 to y2, x3 to y3, etc. And then scalar multiplication, a times a sequence of numbers, our scalar just multiplies each coordinate. So ax1, ax2, ax3, etc. I think it's kind of an odd looking notation, but you can consider this f to the infinity sort of like an extension of f to the n. So like if f is equal to r, then r to the infinity is an extension of Rn. Those are our vector spaces of dimension n. So c to the infinity then is an extension of c to the n, and it's just a bunch of complex numbers, z1, z2, up to z infinity. So for now this sequence of complex numbers, we want the limit to approach 0, and this is the limit being 0 in the same sense you did sequences in series in first year calculus. So we want the limit as n approaches infinity of z1, z2 up to zn as n approaches infinity to equal to 0. So these numbers then should close in on 0. And I just gave you a quick example to remind you of what you had done in first semester or first year calculus. So our an, we would define our sequence something like 1/2 to the n, so it becomes 1/2, 1/4, 1/8, and you can see that the sequence is decreasing, approaching 0, and we would say the limit as n approaches infinity of an is equal to 0. The first thing we want to verify is the additive identity is in this subset. So the additive identity for this sequence of in is just the sequence of zeros. And we can see obviously the limit as n approaches infinity of in is equal to 0. And just a quick note just to show you why this is how I chose my identity. I considered a random sequence, Zn, and I added my identity matrix, identity sequence. So that would be Z1 plus 0, Z2 plus 0, etc., which is simply equal to Zn. And that was my phone, by the way. The next thing to verify is that addition is closed. So I have two sequences with the limit equal to 0. So I have an, so the limit as n approaches infinity of an is the limit as n approaches infinity of a1, a2 up to an equals 0, and the limit for bn is equal to 0. So now when I look at the limit of an plus bn, that's the limit of n as n approaches infinity. And remember how we add our sequences, it's term by term, so we have a1 plus b1, a2 plus b2, all the way to bn plus bn. But since separately this an goes to 0 and this bn goes to 0, that means the limit for the sum, or for this sequence, will also go to 0. So addition is closed. Next, we need to show that scalar multiplication is closed. Again, we have a sequence an whose limit is equal to 0. When we multiply by a scalar alpha, then we have the limit of alpha a1, alpha a2 up to alpha an. Since the limit of an is 0, then when we multiply by a scalar alpha, we can just basically pull out the alpha, we still get a limit equals 0. So now we have this subset, the sequence of all sequences of complex number with limit 0, and we've shown, because of the additive identity is in this subset, addition is closed and scalar multiplication is closed, then it is also a subspace. This set here is a subspace of C infinity. Our next example, let W be the subset of R3 defined below. We want to verify W is a subspace of R3. So W are the vectors x such that we have x1, x2, x3, where x2 is equal to twice x1 and x3 is equal to 3 times x1. And all of these x's are real numbers. So a quick example of a vector in W, if we let x1 equals 2, that will mean then x2 must be 2 times x1, so that will be equal to 4, and x3 is 3 times x1, so that will be 6. So 2, 4, 6 is an example of a vector that is in this set W. I have all my properties now. So first we verify the additive identity. So the identity for R3 is 0, 0, 0. So x1 is equal to 0. You can see that x2 is twice x1 and x3 is 3 times x1. So the identity matrix is an element of W. We can show addition is closed. So let's say we have a vector x, which is equal to x1, 2x1, and 3x1, and a vector y equal to y1, 2y1, and 3y1. When we add them together, we have our x vector and our y vector. We add component by component, so we get x1 plus y1, 2x1 plus 2y2, 2x3 plus 3y3. So we can have our x1 plus y1, we can factor out the 2, and we get 2 times x1 plus y1. Factoring out the 3, we get 3 times x1, y1. So you see the second coordinate is twice the first, and the third coordinate is 3 times the first. So this sum of two vectors is still in W, so addition is closed. Finally, we have scalar multiplication is closed. So if we have a scalar A times x, then we have A times x1, 2x1, and 3x1. So we have ax1, 2x1 times A and 3 times ax1. So what we have is ax1, then our second coordinate is twice ax1, and our third coordinate is 3 times ax1. So our ax is still an element of W. Since W is a subset of R3, we've shown that it's also a subspace of R3. Our next example, let W be the subset of R3 defined by x1, x2, 1, where x1 and x2 are any real numbers. Show that W is not a subspace of R3. So I should circle this. And we have W is the vectors x, such that we have an x1, x2, and then a 1 in the third coordinate, and x1, x2 are real. So first, we need to look at the additive identity. So the additive identity for R3 is the 0, 0, 0 vector, and this vector is not in W because the third coordinate is 0 and not 1. This alone is enough to tell us that this subset W is not a subspace. So I should say W is not a subspace. And I can stop there. But I'm also going to check the other two just for practice. So first, addition is not closed. So if I take a vector x that follows this form of W, x1, x2, 1, and then I take a vector y that follows this W form, y1, y2, 1, and I adding component by component, I get x1 plus y1, x2 plus y2, and then on the third coordinate I get 2. So this also is not in W because the third coordinate needs to be 1 to be in W. So for this reason alone, W is not a subspace. So if I hadn't checked the additive identity and I just started by checking addition and I found it is not closed, I could just stop there and say W therefore is not a subspace. Let's look at scalar multiplication. So now we have a scalar A times x1, x2, 1. So our vector is ax1, ax2, and then A. So unless A is equal to 1, this vector is not in W. But remember, this should hold, the scalar multiplication closure should hold for any real value of A. So on this condition alone, we can say that W is not a subspace. So there are 3 conditions here, and all 3 of them failed, but it's sufficient just to have one failure to be able to say that W is not a subspace. So we've done many examples now of subspaces. We're going to look at sum of subsets and a direct sum. We will start with the definition of the sum of subsets. So suppose we have U1, U2 up to UM, and these are subsets of V. Now we want to define the sum of U1, U2 up to UM, and we're going to denote that with these plus signs. So U1 plus U2 plus up to UM, and that's the set of all possible sums of the elements U1, U2 up to UM. So U1 plus U2 up to UM is equal to the vector U1 plus the vector U2 plus the vector UM, where U sub I is an element of the U sub I subset. And we'll do an example. This is a fairly easy concept once you see it. So suppose U is the set of all elements of F3 whose second and third coordinates equal 0. And then W is the subset of all elements of F3 whose first and third coordinates are equal to 0. Here I've written what the set U looks like, the subset U of F3. So F3 means there are 3 coordinates. And here we say the second and third coordinates equal 0. So U are the vectors such that we have a first coordinate, which we'll just call U1, and then we have 0, 0, elements of F3. So if these could be real numbers, U1 could be a real number, it could be a complex number. So U is an F. W now, that's the set of F3, so 3 coordinates, whose first and third coordinates are equal to 0. So you can see I have a 0, a W2 for the second coordinate, and a 0. And I just copied, or I just made some elements of U and some elements of W. So U might be 1, 0, 0, where U1 is equal to 1. Or it might be 1/2, 0, 0, where U1 is equal to 1/2. Or it might be I, because it might be a complex number, 0, 0, where U1 is equal to I. For elements of W, I could have the vector 0, 2, 0, W2 is equal to 2, or 0 minus 2i, 0, where the minus 2i is W2. Obviously, since U is the set of all vectors of this form, this is just a subset of U. So these are a few representative elements of U, and these two are a few representative elements of W. There's an infinite number of vectors in W and an infinite number of vectors in U, because U can have an infinite number of values and W2 can have an infinite number of values. But anyway, just looking at these as kind of an example, so one of the possible sums, so remember, the sum of subsets is the set of all possible sums, but one of the possible sums for this U and this W would be to take an element of U and then add it to an element of W. There's another possible element, this element of U added to an element of W, the second element of W. Here's the second element of U added to the first element of W, the second element of U added to the second element of W, then the third element of U added to the first element of W, third element of U, second element of W. So again, the idea is, and in all cases when we add these two vectors, the first element comes from our first set U and the second element comes from our second set, subset W. So this comes from U, the second element comes from W. The first comes from U, the second comes from W. So again, this kind of just follows this definition here that one of the sums of the set U1 up to UM, in this case U1 is U and U2 is W, are the vectors where the first vector in the addition comes from the set U1 and the second vector in our vector addition comes from the set U2. So this would be an example. But we extend this on to UM, however many subsets. In this case, we only had 2, but we can have up to M. And again, here, this is just a sample of all the sums. For the set of all possible sums, there's an infinite number of them. Now, if I wanted to look at the sum of subsets of U and W, I need to consider what a representative element of U looks like, which is U1, 0, 0, added with a representative element of W, which is 0, W2, 0. So it looks like a U1, a W2, and a 0. So this is what the sum of the subsets look like. It's all the vectors of the form U1, W2, 0. And actually, we can rewrite that. The U1 and W2, it looks funny to me, so we could say XY, 0, or we could have done X1, X2, 0. But essentially, it's the set subset of F3 where the last coordinate is equal to 0. For our next example, suppose U is equal to X, X, Y, Y. That's a subset of F4. So the idea is that first and second coordinates are equal, the third and fourth coordinates are equal. And then W is a set where we have X, 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 Y. So the first 3 coordinates are equal and the last coordinate is something different or potentially different. And that's a subset of F4. And we want to find the sum of subsets of U and W. Now when I write my representative element of U, I have the first and second coordinates equal, and then a different third and fourth coordinates, which are also equal. And then for my representative element of W, I have my first 3 coordinates the same, and then my last coordinate different. I do believe that this X should be different from this X. So in other words, I don't think what we have is XXYY and XXXY, so that these will add to 2X. I don't think that's the case. I think this is just showing you that the first 3 coordinates are the same, so I put a subscript to show that they are different. So that means U plus W are all the vectors X such that these first 2 coordinates are the same, so we're going to represent them with X1. This third coordinate is something different from the first 2, so we'll represent that with X2. And finally, this last coordinate is something different from all the previous coordinates, so we'll represent it with X3. So this here is what U plus W looks like. Now we have the direct sum. So suppose U1, U2 up to UM are subspaces of V. So this is different because before we were talking about subsets. So they're subspaces of V. The sum U1 to U2 up to UM is called a direct sum if each element of the sum of subsets can be written in only one way as a sum of vectors U1, U2 up to UM, where each of the vectors U sub I comes from the set U sub I. Our example is, suppose U is the subspace of F3, and again now we're talking about subspaces of F3 whose last coordinate equals 0, and W is the subspace of F3 of those vectors whose first two coordinates equal 0. So then U, the subspace, looks like this, x, y, 0 in F3, where x and y are scalars, and W is equal to 0, 0, z, where 0 is a scalar. That means our sum of subsets, the subsets U and W, is equal to vectors from U plus vectors from W. So that's going to equal to x, y, and z vectors, where x, y, and z are scalars. And again, this is our sum of subsets, U plus W. Now, if someone gave me a vector x, y, z, and they asked what were the vectors from first the set U and then the vector U2 from the set W, I could figure that out, because if it's x, y, z, then there's a vector from U and a vector from W that get added together. Well, the vector from U is the x, y, 0 vector, and the vector from W is the 0, 0, z vector. There's no other vector that does that will give me this x, y, and z, right? So for example, if someone gave me the vector 1, 2, 3, if we're looking at this sum of subspaces, the U vector must have been 1, 2, 0, right? There's no other way that W could have contributed because it has zeros at the beginning. So it all had to come from U, and it's 1, 2, 0. And that means this last coordinate, it had to come from Z. This 3 had to come from the W, so that's 0, 0, 3. So uniquely, there's no other vector from U and W that will give you 1, 2, 3. So what that tells us is this sum of subsets U plus W is a direct sum. And I put the circle around the plus to indicate or denote that we are dealing now with a direct sum. And it also turns out that this U plus W, this direct sum, is equal to F3, because here we can generate any x, y, z, any vector in F3. Our next example, and I think we're getting close to the end of our video, let U1, the set, equal to x, y, 0 in F3. Let U2 equal 0, 0, z in F3, and let U3 equal 0, y, y in F3. We want to show that U1 plus U2 plus U3, the sum of subsets, is not a direct sum. So let's underline that. Now my sum of subsets, U1, U2, U3, gives me an x1, y1, 0, a 0, 0, a z2, and then a 0, y3, y3. And again, I think this y here is not the same as this y, which is why I put indices, 1 for the first U1, the indices of 2 for U2, and the indices of 3 for the third for U3. So then I'm going to get x1, I have a y1 plus y3, and then I have a z2 plus y3. So they're independent of each other. So I really can say they are 3 different elements, x, y, and z, which makes it equal to all of F3. But the question still remains, is it a direct sum? And the answer is no, but we want to show why. And the easiest way to show something is not a direct sum is to find 2 ways to get the additive identity. So we're going to consider the additive identity 0, 0, 0, 0. And the most obvious way is is really always the first way you should come up with the identity, is to let U1 equal 0, 0, 0, U2 equals 0, 0, 0, and U3 equals 0, 0, 0. And you know that these 3 vectors exist in the U1, U2, and U3 subsets because we said that U1, U2, U3 are subspaces, so the identity vector has to be in there. So then what's up to you is to find another way of getting the 0, 0, 0. Actually, I wrote too many zeros over here, so let's get rid of one of them. Okay, so it's up to you to figure out the other way of getting 0, 0, 0. And so what I did is I chose U1 to equal to 0, 1, 0, U2 to equal to 0, 0, 1, and U3 to equal to 0, negative 1, negative 1. And you see my U1 vector satisfies this condition where we have a first coordinate, a second coordinate, and then 0. So a first coordinate, second coordinate, and a 0. U2 satisfies my definition of the set U2, which is a 0, 0, and a z. So a 0, 0, in this case, z is equal to 1. And finally, U3 satisfies this condition of a 0, a y, and a y. So a 0 where y is negative 1, and another y. And also, this just shows you, I believe, that this y is not equal to this y. So in U1, this 1 was not equal to this y over here. So these aren't necessarily supposed to be equal. It's just to show you the pattern within U3 and the pattern within U1. But anyway, getting back to this, U1 is equal to 0, 1, 0, U2 is equal to 0, 0, 1, and U3 is equal to 0, negative 1, negative 1. When you add these together, you get the identity vector, which means there's two ways to sum up vectors in U1, U2, U3 to get this identity vector, which means U1, the sum of subsets, U1, U2, U3, is not a direct sum. Your book has a few more theorems, facts, properties about the sum of subsets and direct sums that I am not going to cover, but if, in case your teacher does, you should take a look at those as well. And that's it for the material in this video, but to kind of review what we went over, first we reviewed what a vector space was, and that was a set V of vectors along with an addition and a scalar multiplication operator that satisfied these properties here, that the vector addition is closed, the scalar multiplication is closed, the addition is commutative and associative. There was an additive identity and an additive inverse for all vectors. There's a scalar multiplicative identity, the scalar multiplication is distributive, and the scalar multiplication is associative. The next thing we did is we defined what a subspace was. So if we have a subset U of V, it's called a subspace of V if U is also a vector space in its own right, and we're using the same vector addition and scalar multiplication for V. So in other words, we have a vector space V, and then V is a set of vectors along with the two operations, but we take a subset of the set of vectors. We keep the two operations, and if the subset is still a vector space, then we call the subset a subspace of V. In the previous video, we went through pains to show that vector spaces satisfy these 9 conditions, but because U is a subset of V, many of these conditions we get for free because the addition being commutative, that's true for all vectors, so it's certainly true for any subset of vectors U. Addition is associative, same thing. It's a property of the operation, not the subset. We have the scalar identity, well, actually not that one. Which one is it? The scalar distributive property and the scalar multiplication property over here, that being is associative. Those are also given to us for free. Once we have these, if we know that the vector addition is closed and we know scalar multiplication is closed, we have the additive inverse as well as the multiplicative identity. So the 3 things that we need to show is that addition is closed, scalar multiplication is closed, and the additive identity is in our subset. So these are the 3 conditions we have. From there, the rest will follow, and a lot of these just follow simply because it's a property of the operations which we borrowed from our vector space V. We did several examples, so I'm not going to do an example here in this overview, but at the very end, we did the sum of subsets. So if we had subsets U1, U2 up to UM, they're subsets of V. Then the sum of u1, u2 up to um, which we denote with the plus sign, so u1 plus u2 plus up to is the set of all possible sums of the elements. That is, the sum of subsets are the u1, u2 up to vectors, where the u sub I vector comes the u sub I subset. And finally, we define the direct sum. So suppose we have our subsets, u1, u2 up to and actually they're not just subsets, it's a subspace of V. Then the sum of subsets is called a direct sum if each element of the sum of subsets can be written in only one way as a sum of the vectors. So that's it for this video. I gave you a ton of examples, so you can let me know if you think we should do less examples in a shorter video. But know that if you give me that feedback after I finish the whole course, then it's probably going to stay the same. But if you're following along the semester that I'm making the videos, you can give me some feedback. So that's it for this video. Thank you for watching.